Growth. This is our exponential growth. We have seen the differential equation dy dx equals, I'm going to write it in terms of t, because we're going to let t be time. Dy dt equals ky. We saw how to solve that by separation of variables. This differential equation describes exponential growth of some quantity. It's often seen in biology to model population growth. It will show up if it's decay, the opposite of growth. In physics, if you're taking physics and have studied radioactive decay, this equation shows up. And if y is the amount in the population, number of organisms if it's biology, number of radioactive nuclei if it's radioactive decay, whatever it is, t is time. What is this equation telling you about the rate of change of the population? At any moment in time, it's changing, right? Because dy dt, that's my rate of change of the population. It's changing, and the rate of change is proportional to the population, the amount that's there. So the more organisms there are, if it's cells in a petri dish, the more cells in the petri dish, the greater the rate of increase. The more of them there are to multiply. If there's just a few cells, well, their rate of increase isn't that big because there's only a few of them multiplying. Are you multiplying there, Rocky? You okay? Sure? Yeah. So this is our differential equation that describes exponential growth. We've seen it all over the place. And we saw how to solve this differential equation, right? Separation of variables. dy over y equals kt. Integrate both sides. If I integrate both sides, I get natural log of y equals kt plus a constant. And then to make it handy, you need to be on top, please. Come in late. To make it useful, we got the y by itself, correct? So what do I do to get the y by itself? Exponentiate. Make each side the exponent of e, which gives me y is equal to e to the kt plus c. But then we said I can play some games and massage this a bit and break up the right-hand side using my exponent rules. E to the kt times e to the c. And that e to the c is just a new constant. Let's just call it c to 0 e to the kt. And now it's exponential growth. If t is time, as time goes up, my population changes. The population might go up if k is positive. It might go down if k is negative. We call k a different name. The growth factor, the growth constant, whatever you want to call it. Your biology teacher might have one name, your physics teacher might have another name, it all depends on whatever the standard is for the discipline that you're applying this to. But the big thing is, if k is positive, as time goes on, your population is, yes, Ellie.
When you did when you got the d, c and the k by itself, how come the dt went away when you multiplied it on one side?
How come the dt? Oh, I lost my dt here. Yep, you're right. Thank you. K. No, wait.
Hanging around for no reason.
Oh, this is okay. Oh, I left out the d. dt. There we go. Thank you. I'd left out the d. That was it. Okay, so if k is positive, then as time goes on, my population increases. If k is negative, it decreases. So we can say if k is greater than 0, I've got growth. If k is less than 0, I have decay. Population is decreasing. Maybe there's not enough food. Maybe the bacteria in the petri dish are poisoning themselves with their own waste products, and they're killing themselves, and they're dying. There more are dying than are being born, and the population is decreasing. So this equation will be our exponential growth equation, and your job, you may be given. Well, let's make this. You got a bunch of variables there. The two main ones that you'll probably be working with are the constant and the k. If you're given the constant and the k, well, for a given time, you can find the population. Sometimes you've got to find the constant. They might not give you the constant. And remember, in this form, c sub 0 equals the quantity at time equals 0. Okay? So we try an example. So let's look at the very first example on your handout there, which says I've got a moose population, and the population grows such that the moose born each year is equal to 10% of the current population. So if I've got 100 moose, I've got 10 new moose that year. How do I model that with the differential equation? What does the equation look like? dy dt equals the change in the moose population is 10% of the current population. What? The moose population is, the number of moose being born is 10% of the current population. So y is the current population, and this is the change. So the change in the population is 10% of the current. So I want this to be just 0.1. dy dt equals 0.1y. Okay, that's 0.1. That's my k. Okay, you can go through and integrate that just the way we did, or if you remember the solution, we know that k is going to be equal to 0.1, and let's say we're starting out at year 1, so that's my initial condition. And you'll often play games with the time, with the year. If the year, they give you an actual year, you can make it start wherever you want, as long as you're consistent. So let year 1 equal or be equivalent to time is 0. I can do that. Does year 1 necessarily have to be time equals 1? It can be whatever you want. If I've got data points starting at year 1, well, let that be my initial condition, times 0. That's where I start counting. So let's talk about my solution. My solution is c sub 0 e to the k t. I know k, and now I know c sub 0. What's c sub 0 going to be? How many moose are there at the beginning? 100. Right? Because you know in year 1 there's 100 moose. So y equals 100 e to the 0.1 t. Remembering, year 1 is equivalent to time equals 0. You just got to keep that straight. It makes the numbers easier. If that bothers you, you could put in a 1 for t and solve for the constant. But there's no point in doing that. It just makes more work for you. Now I've got my model. Now I can answer the question. They want to know how many moose are there in year 20. So how many years have gone by? So if I'm starting at, How many years is it between year 1 and 20? 19. So that gives me, the population is going to be 100. Does it actually say? Yeah, year 20. So E to the 0.1 times 19. That's a calculator problem. These are all going to be calculator problems. You just type that into the calculator, and what do you get?
66.85.
How much?
66.85.
That doesn't sound.
68.
Okay, that's better. 668. Yeah, it's increasing. It can't be less than 100. It's got to be bigger than 100. So you have 668 moves at year 20, which is equivalent to time equal to 19. Okay. Now, what's the problem with that model? I can round. I can deal with that by rounding. Okay. Well, you're right. Well, you're assuming that K is a constant. That the percentage of female moose having baby what's plural of mooses? The percentage of female moose having babies is the same every year. So you're assuming constant K. Ah, yeah. Because what happens? What do you think might happen at T equals 100?
Overpopulation.
Yeah. Will this model eventually break down? How many moose are there at time 100? Type it in. What do you get? What's y of 100? Yeah. 100 e to the...
No, it's not.
Guys, we really
You're being mean. You're trying to convince Ellie that.
So what's 100 times e to the 10? Some big number, right? Finish. Did anybody type it in?
Yeah, 1.9 times to the 6. Isn't it 99?
That's a big number, isn't it? Yeah, you're not going to have, you'll most likely have limits on the population growth. So this model is great as long as you don't run into limits on population growth. Yes? Isn't it 99?
Yeah.
Oh, I guess 99, yeah, because we said, yeah, at time 100, this would be 99. So that changes that number a little bit.
Oh, no, that's what I was
Oh, you did put in 99?
doing.
What was it, 1.6 times 10? 1.9 times 10 to the 6? Yeah, so this model is great as long as you're not worrying about limits on population growth. Are the food resources there to support the continued growth? Are you not attracting additional predators? Is disease not going to be a factor? All this stuff. So this is great as long as it's capable of growing to fill the environment. Well, we'll see in a couple of days another model that accounts for all of that good stuff. And we'll put a brake on the system as things start to overpopulate. That's called the logistic model growth, which I'm not sure if you, I asked last year, I don't think you did that in AP biology, did you? Yeah. Did you do that?
We do anything with math.
We did it, but not mathematically. Like we
Well, what's the point of doing that?
We'll solve it. Get us
Okay,
started.
fine. We will learn how to do it mathematically in a couple of days. Okay, let's move forward. Let's look at one now where we've got a situation where they give you two data points and you have to find the C and the K. You might be told that some population exhibits exponential growth, but this is example 2. They told you that in the year 2010 there are 128 moose, and in the year 2015 there are how many moose? 190 moose. 190 moose. they're growing. The moose population is healthy and robust. How many moose are there in the year 2020? And you are given, you need to be told what model this follows, and you are told this follows an exponential growth model. What was that, Rick? You going moose hunting?
Say it louder.
It's a really dumb joke.
I want to hear it.
It's a really bad one.
Say it.
Go ahead.
Slide over.
Sophia wants to hear it. She's not here. She'll watch the video.
Hey, Sophia.
Hi, Sophia.
I miss you. And
I don't want
Mom.
to hear this joke.
No, it's a joke.
Well, it says how many jokes, how many
Say
moose
it.
are in- I'm saying it, Henry. This is how many moose are in 2020. I was like, I don't know. I don't have perfect vision into the future.
Oh, wow.
Richard Princeton, 2020.
Okay, that.
Yeah.
I'm just gonna pretend you didn't say that.
Yeah. I was trying to.
But this is why we model. We can make an estimate. There's assumptions involved that the growth continues at the same rate and so on, but we can model. So to model this, we need to find the constants, the c sub 0 and the k. We can do that. We have two variables. We can set up two equations. We know that y is equal to c sub 0 e to the kt. Okay, so look at the times. Where do you want time 0 to start?
2010.
2010. So at 2010, we'll call that time 0. At 2015, how many years later is that?
4, 5.
11, 12, 13, 14, 15. 5 years later. And in 2020, that's 10 years later. Okay, so we can do this. All I have to do is substitute in my values, each pair of values, to make a new equation. So let's do the first one. At time 0, I have 128 moose is equal to c sub 0 e to the k. Oh, but good, time is 0. That makes life easy. What's c sub 0? 128, because e to the 0 is 1. So this gives me my constant is 128.
So y and c sub 0 is 128.
Right, because to start with, right, at time 0, c sub 0 is the initial population.
Oh,
So my population at time 0 is c sub 0. But now I've got to put in, but I don't know the k. I've got to find the k now. I'll get that from the second pair. I know that for the second, so doing the second one, y equals c sub 0 e to the kt. I know my population is 190. I can put that in. I know c sub 0 is 128. What else do I know? The e to the, and t is 5.
Couldn't you just do it as one, since we're strictly speaking in terms of 5 blocks?
Do it as
Say-
1.
Instead of 5.
Oh, you say like have time.
Like
Each one is equal to 5. 1 unit is equal to 5 years.
Oh, you could do that.
Yeah.
But
Since
then
you're only-
then you have to, but then you have to go and reconvert at the end. Right? So if you do it in blocks of 5, oh, I see what you're saying.
Yeah.
Okay,
It just
sure,
makes-
yeah.
It just turns 5 into 1.
Yeah, you could. Yeah. Yes, that would work because every increment goes up by 5 units.
Yeah.
If that weren't the case, if they'd asked for the 2019 instead of 2020, then that would work. But yes, you could do it that way. Okay, so can we solve an exponential equation? Remember how to do that from algebra 2? What's my first step there, Mutar? Yeah, divide both sides here. 190 over 128 equals e to the 5k. Then what? Take the natural log. Natural log of 190 over 128 equals 5k. And then divide by 5. So that gives me k is equal to 1/5 the natural log of 190 over 128. I can solve for that. That's just type into your calculator.
0, 7, 8, 9.
Yeah. Okay, and numerical problems on the AP test, a calculated problem, 3 decimal places. We're not, don't talk to me about significant digits, none of that stuff. 3 decimal places to the thousand. And they'll take either rounding or truncating. So we're gonna call this 0.079. What does K represent? K represents, so let's come back to, yeah, let's come back to the original differential equation that we didn't write here because we already knew how to solve it. But it's saying dy dt is equal to ky. That means dy dt is equal to 0.079y. So every year, the number of new moose is equal to 0.079 times whatever the current population is. If there's 1,000 moose, then there's 79 new moose added to the population. If there's 10,000 new moose, then there's 790 moose added to the population. Okay, because the growth rate is always going to be proportional to that constant. Okay, how are we feeling about that? Yeah.
I was thinking of asking about a different way of doing it. Maybe it's the same way, but I was going to say. If you just take the difference in years.
The difference in the years. So,
In the number.
what, 5 years? Yeah.
But it works.
What works? What are you saying?
You saying like just take the slope of the line? It would work for this. It would work.
It does not work here. This is exponential.
Yeah, what I'm saying is it would work for those 2 points, but it wouldn't work between them. Like if you try to model the actual system.
Oh.
I got it.
Well, of course it's got to work between 2 points because 2 points always defines the line. Once you get a third point in there, you're off. It's not linear. Okay, the growth looks like that. If you try to model it with a line between those 2 points, you'll quickly get way off. Okay? If you want to do, you can do an Euler's method, which is equivalent to marching a tangent line approximation along the curve. And if you have a very small delta t, yeah, you'll get there. Also, you can do just a simple tangent line approximation, which as long as the time isn't too far off from the tangent line you picked, you come close. But using this model, we can get an exact solution. And then your solution is only as good as how well the model represents the true physical situation. And that's where the science comes in. Okay, let's talk about half-life. Where's our physics people?
This is bio too.
This is what? Oh, like, okay, so, oh, like dose of medicine decaying in your body? Okay.
Yes.
Yes,
Or
yes.
like radioactive stuff.
What was what? To this one?
Remember.
Oh, we never finished. We got K, so let's finish it up real quick. Thank you. Woo. So we got K. Now the question was, how many moose are there at time 10, which is the year 2020? Y equals 128 e to the 0.079 times 10. Right? And what do you get when you do that? Let's type that in. So I have E 282. Okay, this is the one exception to the 3 decimal places on the AP test. If it's something that can't be fractional, round it to the integer. So if it's 282.01 moose, call it 282 moose. Okay. What if the moose is like just part way being born?
Or we only have like, but it's still a whole move.
No, that's
Fine.
That's more than
Something that cannot Something that you know cannot be a fraction, we're going to represent as an integer. Okay? If it's like the number of people, round it to the nearest integer. Number of moose, round to the nearest integer. Otherwise, 3 decimal places.
I'm just saying you said, like, never mind. I didn't intend anything.
Okay. Half-life. This is where things get a little fun. Fun.
Fun for you or I think that's
Stop.
Got it.
We're going to derive the formula for the half-life. You guys have probably used it before in physics. If you took AP Physics, I'm sure you did.
it's just a candle.
So the concept of half-life is used, or is a concept used when K is negative and something's decaying. So I start with some initial quantity and it's decaying exponentially. The half-life is the time it takes for the quantity to be cut in half. If I start with 100 atoms of an element, how long does it take for it to decay so that I have only 50 atoms left? That's the half-life. If you have 100 milligrams of some medicine in your bloodstream, how long does it take for your body to metabolize 50 milligrams of it? So that you have only half left, that's the half-life of the medication in your bloodstream. Half-life is how long it takes for half the original amount to decay or metabolize or go away, however it's being removed, because the quantity is decreasing, whatever it is that we're modeling. That's a very useful measure in many disciplines, physics, medicine, and so on. So that question?
I think it's used for chemistry.
Chemistry too, yeah. All over if there's a chemical reaction and you're using up one of the reactants, how long does it take for half the reactant to be used up? All over the place. And it's going to be a function of K. Right? Because K is going to determine how quickly the material is decaying. The more negative K is, the quicker you're going to lose material, and the shorter your half-life. If K is just a small negative number, then the half-life might be big. So we're going to figure out how to derive the half-life using this equation, and it'll be in terms of K. So what do you think I might want to do?
Natural law. Well, not right now, but eventually.
Eventually. Well, I want the half-life, right? So if that's what my starting point, what do I want the new y to be? I want y to be half of y. Right? That's the quantity that I want. I want to go from here to half of y. Half of it goes away.
Oh, you have to decide.
Well, what I'm saying... Okay, so let me explain. I'm taking this is 1/2 times y, because I want the quantity to be half. And how long does it take for the quantity to decay to half of it? The half-life. So this t subscript 1/2, I'm using t with the subscript of 1/2 to represent the half-life.
Why is it not 1/2 T?
Because
Like this, the 1/2 is an actual.
right, t is a variable here. Well, what's t? I don't know, whatever you want it to be. Okay, let t be 10 years, then you can calculate how much material is left. I don't know. T sub 1/2, the half-life, is an actual length of time. It's the length of time it takes for the quantity to be cut in half. Okay? Yes.
You just only the one side. Do it for you.
I did. What did I do here? I put in a particular time for t. Don't think of it as I'm multiplying both sides by the same thing. I'm letting t be the half-life. That's the time it takes for the quantity to be cut in half. So at that time, t equals the half-life, my quantity is 1/2 the original. Okay? Now what? divide both equations by 2? I want to get rid of the y's, right? I want to get rid of the c's. What I'm going to do is I'm going to take this bottom equation and divide it by the top one. This is what I'm going to take. 1/2 y equals c sub 0 e to the k times the half-life. And I'm going to divide each side of this equation by the corresponding side here. Can I do that?
Of course.
Yeah. Geometry, right? Division postulate. If equal quantities are divided by equal quantities, the quotients are equal. Yeah, I'm trying to teach my geometry students that. I get the same response from them. If I've got two equations, and they're equal, I can divide one by the other as long as the one I'm dividing by is not 0. I can do that. So what's 1/2 y divided by y? 1/2. What happens to my c sub zeros? They go away. Cancel. What's e?
2.1.
Yeah, I got e to the k times the half-life. Yeah. So what do I have here?
Oh, if you're dividing, you subtract the exponent.
Yeah.
So it's
E
kt
to the
half
k.
minus kt.
Half-life times t.
That's the equation.
Well, we're not there yet. And our goal is to get to this thing here. We got our answer there. We're almost there. I'm going to take the natural log. Natural log of 1/2 is equal to k times t. Now, there's one thing that we need to do. Y is equal to c sub 0 e to the kt. Okay? I can let this t be equal to my initial time. This is a half-life, right? How long it takes for it to decay in half? But starting from when? What's my starting point?
Whatever the origin.
Well, if my half-life is 3 seconds, what was my starting time? 0. That's 0. So I get natural log of 1/2 equals k times t half-life. And now we're almost there. We can finish this now. That gives me the half-life is equal to the natural log of 1/2 over k. That was the goal. That means we did it right because the paper's correct. That's my expression for half-life. And you can go through and you can rearrange it. If you're given the half-life, you can just rearrange that and get k. K is equal to natural log of 1/2 over the half-life. So what does that mean? That means if I know the half-life of some material, I can get the k, and then I can go and set up my equation and find the amount of the quantity at any time. My half-life will let me go in chunks of the half-life. It decreases by half every half-life. If I want to know what the half-life is, I know k, I can calculate the half-life. So try a problem? Yes? Time for one problem. Let's do it. Okay. Radioactive decay. There's our first example. Radioactive isotope decays such that the amount is reduced by 1/2 every 100 hours. That's my half-life. What's my half-life? 100 hours. Oh, 10. Every 10 hours. I misread that. Every 10 hours. That's my half-life. How many grams of 100 gram sample are left after 2 days. I want time to be equal to how many hours? 2 days? 48 hours? I need my, this is not a multiple of my half-life. I need to get the K to put into my equation. I know C sub 0 is 100 grams. I need the K, but I've got the half-life.
That's when you use the equation, right?
Yeah. So K is equal to
1 ln 1/2.
ln of the half-life divided by what?
What?
Oh, ln of 1/2. Oh, you're right, 1/2. Nope. I'm having a spasm here. Ln of 1/2 over the half-life,
Which is 10.
which is 10. So K will be equal to the natural log of a half divided by 10. And you would type that into your calculator and get a value for K. And then you can use your equation. Y equals C sub 0 e to the KT, where C sub 0 is your 100. This number here is your K. And the T is your 48 hours. And you can find out how much of the material is left after 48 hours. I've used my half-life to calculate the decay constant. That lets me get the quantity at any time. Yeah, that's pretty cool. Okay, so we'll stop there. Why don't you guys try for homework, try the second example. That here.
We're going to use the exponential equation itself.
Yeah, you're gonna be using
Second example on page 19. And let's do 1, 2, and 3 on page 20. And so we planned for, what day is today? Wednesday? Thursday? When do we want to do a retake on those? Tomorrow? Monday. We'll retake on Monday.